let's get started. Interesting. All right. Pluto civilization. Okay, yeah, that happened before. Yeah, I remember that one. They can manipulate space-time. Right. At first glance, they seem like normal stones. They were arranged in a perfectly straight line, and each stone has a number engraved on it. The strange part is that every time you blink, the stones change. Alright, sometimes the number engraving on a stone changes. Other times, stones split in two, causing all the other stones to shift over a bit to make room in a perfectly straight line. As you observe them for a while, you find that the stones have a consistent behavior. Every time you blink, the stones each simultaneously change according to the first applicable rule. Simultaneously, okay. So each stone is engraved with, if the stone is engraved with number 0, it is replaced by stone engraved with the number 1. Okay. All right. Then, if the stone is engraved with a number that is even, it is replaced by 2 stones. The left half of the digits are engraved. Even number of digits. Okay. On the left stone, then the right stone. Are they engraving on the right stone? Okay, so if it's a 10, don't keep leading zeros. So 1,000 gets split up. The left stone becomes 10, just 10, and the other one becomes 0, 0, no leading 0, so it becomes just 0. If none of the others apply, the stone is replaced by a new stone. The old number is multiplied by 2024. All right, and let me guess, we have to do this a lot. After 25 times. All right, seems easy enough. Yeah. So for each, of course, it's not optimal, but each with 0 becomes 1 if it is okay. And then we do log 10. Our numbers were so sorry, 10. Boom. Is it down or up? Let's see. So this becomes 0. Now we need one more. So 1 plus. This has a the first number is 0, becomes 1. The second number is 1. We have how many digits? 1. There's 2, 2, and then 3 digits. Okay, yeah. So if this number is divisible by 2, and then this is number of digits, just assign it. If this is divisible by 2, well, if it's not divisible by 2, we know that we just move on to the next one, which is multiplied by 20 or 24. Otherwise, and close it. The other way around, yeah, 10 and 9 get split up. 99. Let me put in like this. Maybe, yeah, leading zeros. There you go. So we take so let's first do the left part. Left part means number of digits 10 to the power divided. Well, no, divided. Do we? Not divided. Yeah, divided. Oh, right. We have to divide number of digits by into. So that will, in our first case, yeah, doesn't matter. And then this will give us the multiple here. Okay. And the other one is 1 and 99 because I changed it a little bit. And the other one is, so we still have the number minus to remove 99,000. We do modulo m, right? No, that's not right. M, right, because I haven't done it yet. Let me just copy it here. Yeah. So that means it's modulo reversed. This is our number. And I don't think I need this anymore. And flattened. And let me change this back. So we have apparently this is the example we take. 25, 22, 53, 1017. And if we run this power 2, what? All right. This. Yep. All right. 2 gives us 25302024, and 6168. 3 gives us that. Let's go all the way to 6. Let me just search for this number here. Yeah. All right. We need to run this 25 times. 55, 312. How many times you? Yeah, so this is obviously not optimal. Yeah, let me guess, we do 1,000,000 times. That doesn't sound that bad. 7.5. I mean, it's not perfect, but so at best, half of the numbers get split up on average. Every time you blink, approximately half of the numbers, let's say, gets doubles in price. Yeah, all right. So it will be a big number. All right, let's think about it. So if we get to 0, we go to 1. Yeah. I mean, if we have repeated numbers, like if we have yeah, then we could just drag them all and just count how many there are of those. That's one optimization we can do. I don't know, actually. Let me still run it. So again, for part 2, how many stones after blinking 75 times? Let me just try something. So, how many numbers we have here? 8. So we have 8. Now, at every step, we let's say half of the time, half of the numbers get doubled. So half of the numbers twice 2. What am I doing here? Multiply by what is it? Half of the numbers get doubled, so 3 seconds, right? Divide by 2 and times 3, right? So in our case, with 2, we started with 3, then power, something like that, and then after 6 times, we had like 22 numbers. Sounds about right. Let me try this one. How many zeros we got here? 22. 22 exactly. Nice. Well, 22 numbers, and that's what my formula predicted. Okay. Maybe it's actually quite close. Then after 25 times, 550. No, it's this is a huge error. 50,000 after 75 times is gonna be a lot of numbers. Okay, and in my case, I start with, again, how many zeros it was? 8 numbers. So if we start with 8 numbers, oof, yeah, that's a lot of numbers in our number of stones. This is approximation, so obviously we don't know for sure. Now, we really don't want to keep every one of them. Now, the fact that we multiply by 2024 is a big number, not a prime. This is some mathy stuff. What are the chances that a lot of them are like duplicates? I don't like that we're multiplying by 2024. That sounds like a big number. So my thinking is, can I have an array of numbers that says a bit array? Now that will create a lot of... Well, these numbers are not going to be big. Here's the thing. Well, I mean, let's say we have even this, right? 5-digit number. 5-digit number, which is, how did we get it, by the way? Oh, we multiplied 2024 by 7, right? So we took 7, it wasn't matching any rules, so we multiplied by 2024, boom, we have a 5-digit number. Then we multiplied by 2024 again, because it's still a whatever, and we have an 8-digit number, and that's odd. So we right away we do reduce it. Right away we reduce it into 2 smaller numbers. Yeah, these numbers can get quite big. So we start with 512. Then we multiplied by 2024, we get 7-digit number. That's still not enough. So we have this 4, 5, 6, 7, 8, 9, 10. Yeah. Yeah, what happens if we, so yeah, obviously this is not good. That's a big number. Don't know. So my first thinking was, can we count number of count. Oh, so the order, by the way, doesn't really matter. The order doesn't matter. So we can like sort it even, doesn't matter. So maybe we can, yeah, so initially my thinking is, can I have an array where it's basically whatever the reverse of iota is, right? So for example, if I have 3 and a 7 and I don't know, 1, that's really just 0, 1, 0, 3, something like that, right? So that's a iota. Wait, what? Oh, sorry, here, it's a bit array, right? Yeah, bit array. So whenever we call iota on it, yeah, index 1 and index 3 there. But I don't want to be creating arrays this big. This looks like a big number. Now, of course, what are the chances that we multiply by 2024? So that's once. So we start with 7, right? Even a small number. Multiply by 2024, we get an odd number of digits. So we have to multiply by 2024 again. And my thinking is, can we just keep? Yeah, there's a bunch of 2s, so we don't have to keep all the 2s around. We don't have to keep all the 2s around. Now, this might work if we have something like we can memorize, yeah. Yeah, what if we can do some sort of memorization? So, for example, if we start at 0, right? Well, yeah, so we start at 0, 1 number, right? 1 number creates a lot of, just starting at 1 number, right? Already, that's all. After 75 steps, we have this many stones. That seems like a lot. I don't think I can keep that in memory. But a lot of them are going to be 0s, 2s, 8s, whatever. Actually, this is already pretty bad, right? So if you start with 2, that's odd number of digits. So this will be multiplied by 2024. This one will be multiplied by 2024, etc. Yeah, so the bit array might be iota, I don't know, 10, and we don't want 0, so iota 9 plus 1, right? Yeah, 2024 multiply each, right? For every one of the 0 1 to, from 1 to 9, we have to multiply by 2024 because they have odd number of digits. Yeah, some of them become 20 and 24, 40, 48, 60, 72, 80, 96, etc. But the other ones are all odd number. Don't know. This requires some sort of trick. And then try to implement it in APL. Let me try something. So when we ran it 25 times, right, we had like a lot of numbers. Let me just try to experiment here. Running it 25 times, right, we had, number did we get? I guess it's somewhere here. For me, 18,000, yeah, 200,000. What if I did a, like, unique? How many unique numbers are there? Only 300 numbers. There's only 300 numbers that I actually need to keep track of. That's it. Let me actually do this every step, right? If I, let's say I were to keep track of all the unique numbers, right? So we started with our number. At every step we do the operations, but we only keep the unique numbers. And then separately we'll keep the multiplier. What's your problem? Oh, right. Yeah, 300 numbers. What about if we run it 35 times? That's it. All right. What if I did 75? It's still about 3,000 unique numbers that I need to keep track of. Okay, no, this is easy then. All right, okay. So effectively, even though we have a number of numbers, stones, there's only 4,000 unique numbers after 75 steps. A lot of them are going to be twos, 40s, threes, zeros, threes, etc. because we're splitting up numbers. Yeah, okay. So this seems easy, and I just ran 75 times in 75 steps in 300 steps. Yeah. So here's what I will try. So let's take this number because I think this one is good. Right? So I start with this, this number, we don't repeat it, right? And our operation we take, yeah, so we'll take this, we'll keep it as a separate function. This is 1 I don't know, function, right? And it does this stuff. This is just for one digit, right? So f each for w, right? So this is the previous step where are there any duplicates? Oops. There's already 7. What are the duplicates? Oh yeah, 40, 48. Okay. Yeah. All right. So let me start at this one actually, because this one is all unique. So we'll say one of each, right? 1, 2, 3. Yeah, anyway, doesn't matter. So one of each. Then we run our step for each function, right? We get this. Now the count. So these are the new numbers, right? Now what do we do here? We want to see how many repeated numbers. So, but we know that there's only one of these, so we don't want to lose count of how many actual numbers. So, in our case, actually, yeah, let's do a better example. This one. And here, 2024, there's 2 2s. Yeah, okay. Yeah, so this, let's do it like this. We'll change this one, and I'm gonna move 2 right here. So going to remove. Yeah, so basically the same thing, except we're saying first number. Yeah, the order the order doesn't matter. So I just reordered them. It doesn't really matter. So we grab so there's 2 2s and one of all the other numbers, right? So then we process it, right? We get this. So there's, for example, 40 48, but 40 48 is repeated twice, so we need to count it twice. So there's 2 of these numbers. So the resulting is also 2. Now, can we do iota length of number? So here's my thinking. These are the order number groups, and because of the number groups, we can then sorry. No, I don't do this. I need to like unify it. All right, sorry about that. Okay. So these are the numbers. whatever is repeating, and we know that there is going to be repetitions. 4048 is repeated twice. Where's 4048? Yeah, there's one 4048 right here, right? And it was repeated twice because we know that we started with two twos. So we, not the best example, right? Were there any other duplicates? Let me see, maybe this is a better example to run with. Okay. Yeah, okay. 2 times 2 minus. Versus 2. Oh, there you go. Yeah. So I want to have an example where, yeah, I think this is better. So I wanted to have an example where we actually have multiple numbers produced from different sources, right? So in our case, we start with this, and the resulting is the input will be this, and I'll just get rid of the which one was 4048. Yeah, perfect. So we'll get an 8, we'll get a bunch of zeros, one from here, one from here. We'll get a bunch of I don't know what else we're getting. A bunch of, there's a lot of 2s that we're getting. Where are we getting 2s from here? There's a bunch of 2s coming in here, right? We're gonna get a 2 from this part. We're gonna get a 2 from this part. Perfect. Yeah. We're gonna get a 3 from here. There's gonna be a 2 here. No, this is perfect. So many duplicates. But we'll start with this. Yeah, and yeah, so there's a bunch of 2s. I need to like basically flatten it and count, but it doesn't, that's not how that works. I need to keep count somehow. I need to like merge. Yeah. So yeah, something like that. And I need to, I think it's like hash reversal, right? For each of these numbers, we have a count, and then we say, hey, just flip it around. How many counts? Merge. Yeah, not even just merging by key. Oh, can I use key here? To run the step function for each number. This could be part of the thing. How do I merge these? Okay. No. I don't know, this would be easier to look at. No. what if I each, what do we get? No, each, comma, each. No, that's not gonna work. I don't want to okay, reshape and then split up. Yeah, and then for each one, each, yeah, I don't know. This is bananas. Yeah, and we, no, not here. We're losing stuff. Hold up. Did I just miss a bunch of stuff? Yeah, I just missed a bunch of stuff, so that's not good. Yeah, there you go. And then we just reduce it and something like that. Right, so we're saying one of this, what, 4048, or one of it, well, do we have, no, 4048, we have one, that's not true, 4048, right, shit, we have two 4048s, is it this one? Hold up. One, two, three, four, five, six. Okay. Crap. Okay. 1, 2, 3, 4, 5, 6. There's two of those. Right. 4048. There were two 4048s. So we got 40 and 48 as a result. And for each of those, we got two 40s and two 48s. I think there's a better way to do this, but then we reshape, raise like this, and I just need to merge number and count. I don't know, this is really ugly. I think there's a better way. Oh! No, that's still not good. I think there might be a way. Okay, hold up. So we have numbers. We have flatnet and unified, right? We have the unique numbers. Then these are all the uniques. Wait, why do we have? Oh, we have another 4048. Yeah, so there's only 1, 2, right? So for each group initially, no, for each n, does it, what do we, if I have to, no, it wouldn't, each number would not, no, it could have 2, right? If we had 22 or something, then we'll get 2 2s. Okay, no, that's, we need to unify count for each number. For each number. Yeah, this is complicated. For me, at least, I don't know. It'd be nice to have like a hash table or something, but alas. So these are all the unique numbers that we got. We'll call them U, right? Let's go back to N. So I only want to have U, unique numbers, but I want to keep track of all of the all of them in terms of groups. I want to keep track of both these things. Yeah, honestly, what I was doing before would be nice if I had both numbers okay, so we have numbers and each with alpha. Would that work? Yeah, something like that. I don't know. That's kind of dumb. Well, this might work. This might work. And then we disclose. So now we have unique numbers and so if we raise, reshape, and then whatever the opposite of raise is, then we have numbers and their counts. So now if we run a key, that work? Yeah, okay. So this number, we have one of it. Except, of course, it's not just I think it's just this. Okay. Oh, this is perfect. This is exactly what I need, and I just need to disclose it. This is exactly what I need. So 2028, whatever this was, one. We have one of it. For twos, we have 4 times 1. 40, we have 2 of it already, and only once. Yeah, perfect. So this is that. And we might even keep it that way. I like this structure, right? Because we can easily get, nah, let's just keep it dumb. Okay, how do I split it into reshape, split? Yeah. And reverse. All right, so we have the new numbers, okay? Yeah. Okay, so I think that checks out. And two. Just need to test it. Yeah, so this is the new input think that works. Yep, okay. So let me try something. So we start with this and 1. And not like this, but rather count, I guess, yeah, count and numbers, right? We get input, checking, count is 1, numbers are that. Then we run, I guess we didn't even need this, haha. For each number, yeah, for each number, we run f on it, and that's our new number. Well, it's not a new number. Ooh, okay. Right. And get 1, whatever. So we take the count and we reduce each. But come on. That's what I did here. That worked perfectly fine. Each. Yeah, why can't you do that for me? Disclose? Oh, disclose, yeah. Ah, come on. Reduce, disclose. Why can't you do that? Right, because it turns into an array. Yeah, okay. So I think this. Yeah. Okay. Right. Oof. Right. Then we don't need to do this anymore. No, I think I'm making a mistake here. Just go like this. Yeah, I can't be disclosing here. No disclose. So I think it's just this. Oof, okay, all right. So we run a function on the numbers. We have 1 of each, supposedly. Right. Yeah, all right. Supposedly. Yeah. Then I'm just building this up again. And now, yes, we do reduce, disclose, so just tuples, array. We do the trick here to get us just the numbers. Reshape, right? Because we want to do the key on still the same things. W, right? Disclose and then reshape. And split. Okay, so we get 1. Yeah, and then we have to do the flipping thing. It will always be like that, so maybe I should actually count like this. That'll work. Yeah. Okay. Power 2. Now we have 253, 0, 2024, whatever else, each one time. If I run it 3 times, these are still unique, but still the same numbers. If I run it 4 times, we will have duplicate 4s. Yes, there's a duplicate 2s. Yeah, if I run it 5 times, I should get kind of all those numbers, but now we have 48s, yeah, and then if I run it 6 times, yeah, I have one of the first number, one of the next number, one of the 48, and for 2s, I have 4 of them. 1, 2, 3, and 4. Yeah, there's 2 4s. What about 0? 0, we have 2 as well. 1 here and 1 there, yeah. 4, there's only 1 of 4s. Yeah, no, this is quite doable, all right? So when I ran it 25 times, we take the count and sum it all up. Come on, this close. 5, 5, 3, 12. Yeah, okay. So I think we're ready. Oh, I was running it on production. Ah, right, DOI. Start S1. Yeah, 18, 90, 92. And then if I just run it 75 times, wow, it's pretty fast. Yeah, okay. That was pretty straightforward. Surprised. I don't need any more optimizations. Yeah. This is our function. Yeah, this is the same thing. It was way shorter, yeah. This is so complicated. So we have a count, we have a number. Have a number, we have a count. We call function on on the numbers. Then we append it to each of the counts, prepend counts to each one, reduce, reshuffle, so we have the all of the counts and all of the numbers. Then we reverse, so we can do the key on the unique numbers, not only on all the numbers, and we just need to sum up all of the counts for that number. So now we have counts and numbers. We because we did a reduce, so we have to do this thing, disclose, and just turn it into an array of numbers and counts. Cool, that's cute. Can I just like first, does that work? Yeah. And can I replace C with 1 take W? Yeah, that works. Okay. And here I need 1 take. I don't think I need this anymore. Yep. Sum up. Yep. That's a little more straightforward. Run is this function. we take the argument and run it that many times. So run 25, run 75 times, 89, 92, and then a big number. Yeah, not kind of it. Maybe. Will I understand what the hell am I doing here, like in a week? Is the question I always ask myself. Do I need this? Yeah, I need that. The answer is not really. So first of all, these will be numbers. These will be step, right? And R is what? Run. That's why. I don't like that it wraps so much functionality around. Maybe I can keep this outside. It's too optimized. This is not even a step. This is like stone. This is a step of a step. Yeah. Runs it for me, but honestly, it's fine if I provide this number myself and then one, and one. So I can get rid of this, can get rid of this, and it just becomes a simple function. Yeah, I think it's fine to just duplicate it because it's quite clear that both of them are the same thing, except we just run our thing 25 times and 75 times. I guess I could even just to speed it up. It doesn't really make sense, but like we ran it 25 times and then we threw away the result essentially and ran it 75 times, 25 of which we've already done. So technically we could just copy this result halfway through, right? I don't know. And then take the halfway result and run it 50 more times, right? Yeah. But I don't know, this is ugly. It's fast enough, honestly. There's no reason. Yeah. This part, I don't know if I can make it simpler. I'm sure there's a way. Right? So let me just run 5 times. 5 times this number. This number. We run n and 1. Yeah. I already got rid of the funds. Yeah. So is there anything? I feel like this gymnastics right here can be done better. This business can be simplified a little bit. I mean, already I know that we can, so this will fail, right? I don't know. But already I think I can make it simpler. So count and n assigned, we take this, and then this becomes just a count. Yeah, that doesn't really help. Is it the same thing? It's not even the same thing. Right, because it's n and then count. That's why. And then like this. Same thing. Doesn't really, well, helps a little bit, I think, for clarity. Numbers and count, take it from the input. We just take the first one, which is a number, run a step function on it. What if our step function returned the count for us? Because that would simplify this step. No, but even still, so we have accounts and numbers, and then this whole thing, I feel like even this can be optimized. So let me just copy this for now. So we got this, right? And of course we need to disclose, well, that's a big chunk of it actually. Yeah. But okay, no, hold up a minute. Can we? Yeah, it doesn't work. What if I just had step, right? Which, yeah, and I ran a key on it. Yeah, I'd be like, yeah, I saw 2-0. Yeah, that's not good. So I need to run a key operation on it, right? Because that will, is there a better way? I really like to use the key here, but maybe there's something else. Key is so convenient. I just add up the counts, so easy. For each unique number, I add up all of their numbers, all of their original number things. Okay. Can I do like check for twos and all the indices? Is that a thing? No, that's not gonna work. That would have been nice. Check all the twos. Maybe that works. No, that doesn't make sense. I mean, it's fast enough and short enough. If anything, should be optimizing the step function. Call it 1, I don't know, it looks better. 1 stone. Stone. 3-letter word for rock. Okay. For stone. Gem. No. Pit. Okay. That would be nice if this was like gem. Something. Then we, I don't know. Yeah, 1. It's fine. Okay, so number count. Take the first one, which is number. Run 1 on each. Yeah, I guess 1 doesn't actually do 1. It actually does a step. So 1 is a blink, right? This is a blink. Blink. And then we just want to keep like, I don't know, numbers and stuff. Yeah, I think there must be a way to like make this better. Anyway, so we blink, put a C right next to each one, disclose, reshape, reverse. So we have for each number, really we have for each number, I want to get the counts, because then I have the key operation, which will make it so much simpler. Again, I'm gonna spend like 5 more minutes on this. Defense, display. So if we run it, what is it? 125, 117 with a 1, and we run it 6 times. I don't know. Right, we get that, and then let's say we want to run it 1 more time. So we have the number count, take from omega, take the first one, so that's the number count. We'll do the blink each. Let's just do that like that. I think doesn't really help. Blink each, right? So we have that. Um, 0 times count plus, yeah, and flatten it. Numbers. Yeah, what if I do this? Numbers and then number. What did I do? Oh, got rid of it. Times 0, count plus, and flattened. Yeah, and then the other part is count, and the other part is just flattened numbers. Yeah, okay. All right. And then we just run a key on this. And since they both have disclose, so then we can just disclose it once. Now we don't need the brackets at all, and or here for that matter. What's the problem? Ah, right, because I didn't actually give it a function. Sum of W. Yeah, still need to do the disclose. Maybe this is a better format because key already gives us a really good format. I like this format more, honestly. Let's keep it this way. That way I just return this. That'll be so nice. This is a better format. Numbers and their counts. That's it. Yeah? This is a better format, for sure. So 125, well, n. Can I do that? 1. Yeah, let's keep it this format. I like this more. Just common one. It's longer, but better. Yep, all right. So 125, 17, right, or whatever. And our function will take the left-hand side, the numbers, blink each. I don't know. Yeah. So that's that. We still need to. Okay, so that's the new numbers. Then we multiply it by 0 and add the counts. Right, it gets replicated. Perfect. I mean, ultimately, I just want to replicate it, and that's the best I can think of. Multiply by 0 and add the numbers. And then we have this, and then if we keep the numbers, what do we have? We have that, which if we were to flatten each and then key on, then we get this plus some, and then we're done. Then we're done. Yeah, I like this more. This is much shorter. Much shorter. Does that work? Run. So of course we need to do this. I mean, honestly, we could do that as part of this thing. And yeah, it's much shorter and I think cleaner, honestly. Just copy of this, and then here it would be give me the yeah, that still works. Is it faster? About same numbers, 89 blah blah 2259. Yeah, sounds about right. Okay, this is way better, shorter. Get rid of this one. Feel like I should maybe optimize this, but I don't know, that's fine. We count number of digits plus 1, that's number of digits. If they are odd, then we just multiply by 2024. Otherwise, I don't like this, 2024 multiply. Otherwise, we, what am I doing here? Right, we create two numbers. This number, which is number of digits divided by 2, 10 to the power, yeah, I don't want to stringify it, modulo the original number. Yeah, I don't know, same. And original number divided by the modulo, not the modulo, the divisor. I don't know what this is. What kind of number is this? Flattened, or not flattened. Yeah, whatever. Yeah, I don't know. That looks fine. Then we do a blink on each number. We assign it to number. Oh, I don't even, oh, this is so nice. I just use it once again here, and that's it. So we take the number. I feel like this could be done better. But yeah, multiply by 0, so we keep the shape only. Add to it the count numbers, which will be basically replicated. And then we flatten both this and n, which is all the way here. That's a little spooky. I don't like that. Flatten both and key on the number, unique number, and its counts. Yeah, this is so nice. The actual run function is so simple. My goodness. My goodness. Okay, I'm done here. Thank you so much for joining, and have a good Wednesday or whatever it is. Yeah, Wednesday, I guess. Bye, all.